So in the last class we discussed about Schmitt trigger. We will start from there itself. Schmitt trigger itself. Okay. So last class we discussed Schmitt trigger. So Schmitt trigger. Okay. So as we discussed, this is a simple comparator which is hysteresis. Okay. So this will act so right like a comparator. But the output of this Schmitt trigger that will be changing its value whenever an input voltage exceeds certain voltage level, which we called as upper and lower threshold voltage. So this is having the property that the output output voltage output voltage changes output voltage changes whenever whenever input voltage voltage exceeds whenever input voltage exceeds certain voltage level. Okay. And this level, which is the upper threshold voltage, upper threshold voltage, and lower threshold voltage. So with respect to this upper and lower threshold voltage, this output is going to change. If your input is going beyond that upper and lower threshold voltages, then the output of the voltage changes. That is the action of this Schmitt trigger. Okay. And there are basically two types of trigger. Okay. One is inverting Schmitt trigger, and the other one is non-inverting. So this is just depending on where you are applying your input. Okay. Depending on that, we'll be having inverting Schmitt trigger as well as non-inverting Schmitt trigger. Now I will be discussing about that inverting Schmitt trigger. Non-inverting you can find out by yourself. So for inverting case, was string Schmitt trigger. So for inverting case, for inverting Schmitt trigger, so the circuit diagram for this one is op amp with a resistor and a feedback resistor. One here we will apply this signal. This is the case for inverting. Here is the non-inverting. Oh, we are considering inverting case. So the signal should be applied at the inverting case. We have a signal. This is the Schmitt trigger in inverting configuration. So this is nothing but an inverting Schmitt trigger. Okay. So what will happen to this output? You consider this as your output voltage V out, and this is your V in. Okay. So V out will be equal to V F minus V out. Sorry, V out. This is V in. Vf minus V in into open loop voltage gain. In this particular case. Okay, so if you consider the difference, multiply with that open loop gain, you'll be getting. For this is especially for the case of comparator, we use this formula, and V output will be nothing but uh, this differential voltage when you're considering that in case of comparator. This is equation comparator, and this will be equal to, in this case we have can also write V AOL minus V in plus Vf. Same expression I have just written. Okay. This is for the case of comparator equation. You can consider this equation for comparator case. And if you consider this as your Vf, in this case, that is the feedback voltage at this point. And in that case, if you calculate that voltage, the voltage voltage across voltage across R feedback voltage R1. The voltage across R1 is nothing but feedback voltage, which is this particular output is connected to the input through this feedback network R2. So the voltage across this R1 will be equal to is the feedback voltage, that is nothing but R VF equal to R1 divided by R1 plus R2. Now, this voltage, if you this as now, this side we have F. So Vf will be equal to, that will be, use that voltage divide method. So Vf will be divided this junction, and that will be equal to R1 by R1 plus R2. And the to calculate this upper threshold voltage, upper threshold voltage upper threshold voltage. So this upper threshold voltage, what is this voltage? The input voltage exceeding in positive direction. That is the upper threshold voltage. Okay. So the input voltage exceeding in positive direction. Okay. So this value of upper threshold voltage, that is the value of V in, that forces the output to make the transition from plus V saturation to minus V saturation. So this is the voltage. Let's say this is the value of V in, or voltage at V in. That you can also write this as a voltage of V in, and that forces output to make transition make from plus V saturation to minus V saturation. So that means if your V in is more than this value, this upper threshold voltage, your output will be going from plus V saturation to minus V saturation. Okay, so that is the upper threshold voltage. So once your input value, the input is going beyond this upper threshold voltage, then your output will switch from plus V saturation to minus V saturation. And this is the case for the inverting Schmitt trigger. When you are having non-inverting Schmitt trigger, just opposite to this will happen. That is, when your input voltage is more than the value of input voltage is more than this upper threshold voltage. In the case of a non-inverting Schmitt trigger, in that case, the output will be going from minus V saturation to plus V saturation. So this is in the case of inverting Schmitt trigger. Upper threshold, if your V in is more than upper threshold voltage, your plus V saturation will shift to minus V saturation. In simple notation, we can say that this under this condition, we can say, just take it in bracket, when your V in equal to, or V in is more than this upper threshold voltage, okay? In that case, your plus V saturation V out shift from plus V saturation to plus V saturation to minus V saturation. So this is the case for inverting Schmitt trigger. Okay. But for the case of non-inverting case, just opposite will happen. When your V in is greater than V upper threshold value, upper threshold voltage, then your V out will be shifting from minus V saturation to plus V saturation. Okay. For non-inverting case, this opposite of this will happen. That we already discussed when we discussed about the Schmitt trigger basics last class. Okay. So that is the scenario. Now, if you calculate uh, the upper threshold voltage, let us say when your V out equal to plus V saturation, let's say, actually, let's consider your output voltage is at plus V saturation. In that case, what will happen? Vf will be equal to V upper threshold voltage. Here we can V upper threshold voltage, and that V upper threshold voltage will be the upper threshold voltage. That is the upper threshold voltage V ut. That will be equal to R1 divided by R1 plus R2 into V saturation. Okay. So this you can find out from here. When your V out, for example, here, when we are V out is equal to, here let's say V out is equal to plus V saturation in the circuit. So what will happen to this VF? VF will happen to this VF. VF will be equal to, but as we discussed here, VF will be in this equation you consider VF will be equal to R1 by R1 plus R2 into V out. Okay, so now in this case V out is equal to plus V saturation. So this will be implies VF equal to R1 by R1 plus R2 into plus V saturation. Okay, because your output is now at plus V saturation. And since you're having this plus V saturation, then you will be this will be equal to your VUT. Okay. Only when once this your input this V in is going beyond this V saturation, sorry VUT upper threshold voltage, then only it will give you the output that will be shifted from this plus V saturation. Okay. And until that condition, if you are having output as plus V saturation, it will remain in plus V saturation until your input is going to become minus V saturation beyond this upper threshold. So this upper threshold voltage is nothing but R1 by R1 plus 2 into plus V saturation. How this is happening? Suppose your input, this V in is going beyond this value, VQT, means that V in is greater than V. Then your this plus V saturation is going to become minus V saturation. How that is happening? Because your VF is VF. Let's say this is VF. VF is nothing but your VUT. Okay. And once your V in is going to beyond that VUT, which means that it is going beyond VF, right? Because your VF is equal to VUT, upper threshold voltage. So once it is going beyond this VF, your negative terminal will be having more potential in this case under this condition, and because of that, your output will be shifted from plus V saturation to minus V saturation because your inverting terminal is having more potential. So then your potential is going to change from plus V saturation. In this case, we will be having transition of the output from plus V saturation. Okay, because your inverting terminal is having more potential under this condition. Okay, and because of that, your output will shift to minus V saturation. Yes, that's why we are taking this VF as VUT, because once your input voltage Vin is going beyond that VF, then only we will get this plus V saturation that is going to shift it towards minus V saturation. So this is your upper threshold voltage, which is also equal to VF plus V saturation, R1 by R1. So once your input is going beyond this upper threshold voltage, your output will become minus V saturation. That you can get from the diagram. Same thing that you can calculate from here also. Second case, I will just here. So if you are considering your V out is equal to minus V saturation, then what will be your VF? In this case, VF will be equal to R1 by R1 plus R2 into minus V saturation. Your VF will become R1 by R1 plus R2 into minus V saturation. And once your V input is going less than that of this V, we call it as a lower threshold voltage. That the voltage at so let's say first F at this time equal to R1 by plus R2 into minus V saturation. So I will take this as minus R1 by R1 plus R2 into V saturation. Okay. And this will be equal to my lower threshold voltage. And once your V in when your V in is going less than that of lower threshold voltage, okay, what will happen? What is that meaning? That means it is less than that of VF, because my VF is now the lower threshold voltage. Okay, so if it is your V in is less than this lower threshold voltage, it is less than VF, which means that VF is larger than your input voltage in. So in that case, your non-inverting terminal will be high potential at high potential because VF is larger. Okay, so this is the VF potential. So VF will be larger as compared to your VE. Okay. In that case, you will be shifting from minus V saturation to plus V saturation because your comparator or the positive terminal or the non-inverting terminal is having more potential and your output will be plus V saturation. This we discussed when we discussed comparator operation. So when your positive part is having high potential, you will be having that plus V saturation. When your negative terminal or inverting terminal is having high potential, then you will be at minus V saturation. So under this equation that we already discussed that comparator. And it depends on this difference values. If your VF is larger, then you will be ending up with positive value at your output. If your Vin is larger, then you will be ending up with a negative value of the saturation because your L is very large. Okay, so if you are taking the difference of these voltages and making that gain, that much of gain, then it will go to that saturation level. All these things we have discussed in the class. So that is what is happening here. So it depends on what is your VF and VN potential, VN potentials. Depending on that, your sign will change, and because of that sign, you will be shifting from plus V saturation to minus V saturation, and that saturation will be given by the high copper. So in this case, also we can have the same kind of scenario with this explanation that I have done here. So the output will be going to shift from minus V saturation to plus V saturation depending on our input. Okay. So for lower threshold voltage, we already calculated that. Just I will write here. So lower threshold voltage. So at this time, what will happen? I'll just write it simply. So at this time, what will happen? Your output. I will. This is the case when your input is so this is the case when your input V in is less than V F less than VLT. Or first I will say what will happen. That when your so this is lower threshold voltage VLT. So when your V in is less than VLT, your V out will be shifting out shift from plus V saturation to sorry minus V saturation to plus V saturation. So opposite of this will happen in the case of non-inverting. So that you can write by yourself, and you have to find out what is this equation for upper and lower threshold value. So it is also simple, just that you have to connect input at the non-inverting terminal. So this is the V out that is shifting from minus V saturation to plus V saturation. So in this case also, if you consider non-inverting case, then here, if your lower threshold voltage is going below that, sorry, input voltage is going below this lower threshold voltage, this condition, then your output will be shifting from plus V saturation to minus V saturation when you are using non-inverting Schmitt trigger. But here we are using inverting Schmitt trigger, so that the output will be shifting from minus V saturation to plus V saturation when your input is lower than lower threshold. Okay. So this lower threshold value again, that is given by the LT, which is also same expression, R1 by R1 plus R2. The only difference is we are having a minus sign here. And this term also we call it as the beta. Okay, R1 by R1 plus R2. That is a feedback factor that determines how much voltage is coming back from that output to the input. Okay, and this one is the feedback factor. Back factor that determines how much voltage is coming from output to the input path through that feedback network. And this we can also written as minus beta V saturation. Sometimes this notation used here we can write beta times. This also can be used to represent the same upper and lower values. Okay. So when your output is your V out is equal to minus V saturation, and in that case your VF will be equal to VLT is equal to minus beta V saturation. Here, as long as as long as as long as this V in your V input is greater than this VLT, okay, your output will be equal to minus V saturation. This no change. Once this V in is going beyond this, below this VLT, when it is less than that lower threshold value, then V out will be equal to plus V saturation. That will be shifted from minus V saturation. This is for the case of lower threshold value. When your V in is less than VLT, your output is plus V saturation. So this is the action of this Schmitt trigger, and this is normally we use to remove those noises and get that good signal at the output without having much mix. So this you can also use in some different way to make a square wave from sine wave. So if you are having take this as your threshold value. You have the lower here. Okay, now consider a sine wave. So this is your upper threshold voltage UT. This is your lower threshold voltage. So, now what will happen if you are using this kind of a sine wave and giving to that Schmitt trigger, which is in the non-inverting operation, sorry, in inverting operation, that means you are using an inverting Schmitt trigger here. So you are using inverting Schmitt trigger, IST. So in that case, what will happen? your sine wave which is crossing at this point, that upper and lower threshold values. Yeah. So let's consider this point first. To this point, what is up to this point? What is the voltage? Voltage is at less than upper threshold voltage. Voltage is less than upper threshold voltage. So in that case, your output will be at the plus V saturation, as we discussed earlier. When your voltage input voltage is less than the upper threshold voltage, your output will be this plus V saturation. Once it is going beyond that upper threshold voltage, what will happen? Your output is going to become minus V saturation, right? That we discussed earlier. Once it is going beyond upper threshold voltage, in case of inverting Schmitt trigger, then it will go to the minus V saturation. This is your plus V saturation, your minus V. So it is going to reach at this. And here also we have that same potential. So which means that your input is, this is your input signal, your V in. So when your V in is still V in is larger than UT, so it will remain that minus V saturation. All these points here also we have that all these points, if you consider all these potential, all these points we are having this the same state, and until it reaches at this lower threshold point, that is this one. And when it is crossing that lower threshold voltage, which means that your V in is large, sorry, V in is less than that VLT. You can see here this condition. This condition, you can see that when your V in is less than VLT, that is at this point. When it is going beyond less than that of lower threshold voltage. So when it is going less than that VLT, then at that time your output should shift from minus V saturation to plus V saturation. It will be plus V saturation. So until this point, it will be in the same state. It will be in the same state, and this is the potential. So then once it reaches at this point, it will shift to the plus V saturation. So it is going to shift from minus V saturation to plus V saturation. Now again, this point nothing will happen because it will shift to minus V saturation again once it is crossing this upper threshold value. Okay, when it is crossing that upper threshold value, then only it will go to the minus V saturation. When it is going below that lower threshold value, then only it will shift from that minus to plus V saturation. Okay, so this will remain in the same state until this point, which is input reaches at this potential. Okay, and when it is crossing that upper threshold value, it is going to the negative saturation, minus saturation value. So like this, it will go. So this is how we can get a square wave from a sine wave by using this Schmitt regime, the Schmitt trigger action. Here we get plus V saturation. So this is the action of a Schmitt trigger when you use the sine wave. And as we discussed earlier, in the non-inverting case, just opposite of this will happen if you are using non-inverting. And this is the action that we can get for the case of if you are using that in a sine wave. And there also we have that hysteresis. Okay. Here also we have that. So the input we input which is is a sine wave which is converted into this square wave like action. And if you consider that a series is, I think I have made an error in the last class for the case of uh, inverting which trigger. I have drawn that series is, but I have given that direction in the beginning. So we had some of these series, and I am showing now it is for inverting Schmitt trigger. Okay, this is also for inverting Schmitt trigger. So first we draw for the we draw for this non-inverting Schmitt trigger. Then I have given the case, and it will remain. So this is I will first complete this diagram, and I will explain. Only this first arrow that I have, that is thing that is deferred. Just check that. So for inverting case, it will come. Other things are same. And here it is. So this region is nothing but not a good drawing. And this one, they said this is the VLT, is the lower threshold voltage. This is your VUT, that is the upper threshold voltage. So this is your input, and this is your output. So what is this condition? This is nothing but your V in is this stage V in is less than VLT. Here V input is less than that of VLT. VLT is here. So beyond this, that is less than VLT over threshold value. And when it is reaching at this point in this state, this state is nothing but V in, which is less than V. So in that case, it will be plus V. This point, which is output, plus V saturation. This one is minus V saturation. That is output. Okay. So it will be remaining in that case as your V in is less than V. This point, you can see that this is less than V, greater than VLT, but less than V. So in that case, we will be having plus V saturation. And then once it is going beyond this VUT, just beyond this VUT level, that is upper threshold, if it is your input is crossing this upper threshold voltage, just crossing, then it is suddenly goes to the minus V saturation. Okay? And here it will be minus V saturation. And again, once your V is, in this case, you're having V in, which is less than VUT. So it is here, it is greater than this region. This region have V in is greater than VLT. All this. that case it will be remaining in that minus V saturation. And once it is crossing that VLT, which is less than that VLT, when it becomes less than VLT, then it is going again plus V saturation. Okay, this is the hysteresis for hysteresis. Inverting Smith. Inverting Smith. And as you know, this is your dead band. So that's your dead band. Dead band. And in this dead band, which is also called as the hysteresis voltage, when you take that will give you hysteresis voltage. This hysteresis voltage is given by VUT UT minus VL. This is voltage is nothing but, so I can write it as H. H will be VUT minus VL. That is the difference between upper and lower threshold. That is your hysteresis voltage. That is in between these two, and that band range of voltage, which is called as dead band. So within that dead band, there is no change in state. That is why it is called as dead band. There is no state change will happen within this voltage. Only once it is crossing VUT or it is less than VLT, then only crossing that VLT, then only the state is going to change. Within this VLT and VUT, there is no change in state. Okay, that's why it is called as dead. So this is the overall action of the Schmitt trigger. Okay. Now we will move to the Astable Multivibrator. And there are also some advantages when you consider this Schmitt trigger over the comparator. One thing, if you want to discuss these advantages, then we can say this is having high speed as compared to the comparator in terms of response. Okay, so here because of feedback, which was not there in the case of a comparator. Comparator, you can see, will be just like this. We had that open loop expression for the same. So this is minus this is take cosine minus you here, and you take output from here, and you'll be having that plus those values here. So this is a simple comparator. It will compare this to V, and so the output will be like V1 times open loop. So this output voltage we have, this equation we already given first. That is for this comparator, and it will compare these two voltage, and which one is higher, that will be multiplied with this open loop after taking the difference. The magnitude will be the difference between the voltages, but this direction will be the direction of the highest voltage, negative or positive direction. So it depends on the magnitude of this V1 and V2 will be higher. It's applied in the non-inverting and inverting terminal. Depending on that, your sign will be different. Okay, that is the how this how the output of comparator. So, but here there is no feedback in the comparator. So because of this feedback in the Schmitt trigger that we had discussed just now, because of that feedback, there will be very response will be very rapid. It will be very having of speed of response is increased in this case as compared to I'm talking everything about as compared to the normal comparator. So as compared to the comparator, the speed of response is higher. And also we can say the relay chattering is reduced in this case because of that is hysteresis. Due to hysteresis, going at first here. because we had to cover the stable multivibrator and monostable series. The chapter play you can also see there are many other advantages also. Also, we can adjust the upper threshold and lower threshold value to adjust the duty cycle. Right? I'm not going to list all those things. You can cover it. Adjusting VUT, VLT. We can change the duty cycle. I hope you understood this point. Duty cycle means if you are changing this, for example, that sine to square wave conversion that I discussed. Yes. So, for example, your upper threshold, if you make your upper threshold somewhere here, for example, let's say this is your upper threshold, and if your lower threshold value is somewhere here, so by adjusting this upper and lower threshold, what will happen to this? Your duty cycle will be different. Upper and lower threshold value. So once it is reaching at this point, you will be having this square wave which is coming down to the negative saturation. Okay, and once it is crossing this point only, it is going. Sorry, not this point. Once it is crossing this point, it is crossing this one, right? Minus is. So once it is going cross this one, so like this, you can adjust your duty cycle. So we can also set this value here. Okay, now let us discuss this astable multivibrator. Stable multivibrator. So there is no much difference in the circuit diagram in this case for a stable multivibrator. For this case, it is the diagram will be similar. The circuit diagram is similar to that of Schmitt trigger. A very small changes there. So we have that op amp, then that op amp we have this earlier. There is a resistor which is and and then we have that feedback. These are okay. So the difference here that you can observe is instead of giving an input, we just have a capacitor here. So the previous case we had given input to the negative or inverting terminal, but here we are just connecting that inverting terminal to a capacitor like this, and which is directly connected to ground. So this is the only difference. Don't confuse with the change in this. So we have only the change in this diagram, that is this resistor R, okay, and this capacitor C, and there is no input. So this is the Astable Multivibrator. Okay. So all the actions are same as of that of the Schmitt trigger, but here everything will be controlled by this capacitor charging. And this. Okay, so here we are not providing input voltage as in the case of Schmitt trigger. But what we do, we just give, but giving feedback back to the inverting terminal. So from output we have given that feedback to the input terminal along with this capacitor. Okay, I will explain what will. Okay, so let me see what will happen. What is happening in this case? So we can say, let's say initially the circuit V out is at plus V saturation. Okay, let's say initially that V out is equal to plus V saturation. This plus V saturation means we are applying some biasing voltage here. From that which is coming. Okay. From that it is coming. So don't hope you understood that plus V saturation. That we discussed it very early of the family. So this is the plus V saturation and minus V saturation that we can get that that we are applying. So there is no input voltage that we are applying in this side. Okay, so this output is coming from that voltage plus V saturation. Okay. So initially, let's say the output voltage is plus V saturation, and because of the feedback from, I'm talking about this feedback, because of this feedback, you can see this voltage, some voltage will be taken from this output and given to this capacitor. Okay. And the capacitor will start charge. Okay. So we can say this because of because of because of the feedback, because of the feedback, capacitor capacitor starts charging. You know, this potential is taken, of course, some fraction of the potential is to this capacitor, this feedback. So the capacitor starts charging. Okay. And when this voltage when this voltage reaches reaches um, the upper threshold voltage, upper threshold then the voltage at the inverting terminal, at inverting, right, inverting terminal, at the inverting terminal becomes larger, larger than larger than uh, voltage at non-inverting terminal. Okay. And in that time, what will happen? Your plus V saturation will be going to change to minus V saturation. V out shift minus V saturation. So this is the operation. So what is that meaning? So we are having some feedback circuit here, and through that feedback circuit, some voltage will be applied to this capacitor, and the capacitor starts charging. Okay. And once it is charged, or once it is reaching some potential, which means that this inverting terminal is having potential which is across this capacitor. Okay. This negative terminal or the inverting terminal is having potential which is the potential across this capacitor. So once this capacitor is charging, so charging means it is getting its potential increased. Okay, potential across that capacitor will be increasing every time, and that initially this was at plus V saturation. Once this capacitor is having some potential which is more than that of the upper threshold value, then what will happen? This negative terminal or the inverting terminal is having potential which is higher than that of the non-inverting terminal, because we are having plus V saturation which is fed back through this network also, and that is given by beta times plus V saturation will be at this potential at this non-inverting terminal, that we already discussed. So when this potential is going beyond that plus V saturation times beta, that is upper threshold voltage, which means that it is going beyond this potential which is greater than this non-inverting terminal. This side, the inverting terminal will be having more potential than the non-inverting terminal, and in that case, your output will be shifted from plus V saturation to minus V saturation. Okay. So it's diagram. Historically, I can show that output how it is three. So let's say this is your output voltage. So here we have zero value. Okay. So this is your output. I'm talking about output. Okay. There is no input in this. So in this case, for example, initially we considered that output initially is at plus V saturation, plus V saturation. And in this time, what is happening? Let's say this is your upper threshold value, your upper threshold, your, I mean lower threshold voltage, upper threshold voltage. So this is your VUT, this is your V, and this is your plus V saturation, V saturation. So here we have that minus V saturation. So initially, let's say this is at plus V saturation, V out is saturation. And in this time, your capacitor will be charging because of that feedback network. So your capacitor is going to charge, and once it is reaching its potential, which is at this point, is crossing that upper threshold value. Until that, your output is at plus V saturation. There is no change in that. Once it is crossing this upper threshold value, that means your capacitor is having some charge which is having potential which is larger than upper threshold value, so that the inverting terminal will feel more potential than the non-inverting terminal, because non-inverting terminal is having a potential of beta into saturation, that is upper threshold voltage. So at this configuration, you are having, because your output is plus V saturation, that has to be multiplied with R1 by R1 plus R2, that value. And this potential at this non-inverting terminal will be equal to V upper threshold. Okay. So once this capacitor is having a potential across that capacitor which is going beyond this upper threshold value, which is simply means that the potential at inverting terminal is more than the non-inverting terminal. So at that time, your output plus V saturation will be the plus V saturation minus V saturation. Okay, so from here, plus V saturation is going to minus V saturation, which is crossing this upper threshold value. Now, if you consider the next case, that is this capacitor is now charged, having some potential, and this plus V, this is initially it was at plus V saturation. Now it is shifted to minus V saturation. Oh, this should reach at minus V saturation. Okay. So now it is at minus V saturation. Now the capacitor starts to discharge. Capacitor starts to discharge because we are having a negative potential here because of minus V saturation. So the capacitor starts discharging, and when it is discharging, the potential will be dropped across that capacitor. Okay. So let's say going capacitor is discharging, it is going like this. And it should actually reach at this. So just drawing it roughly. Actually, this like this. That is nothing but a capacitor discharge. So once it is again, so it is reaching at this VLT, that is lower threshold voltage. Once it is discharging, discharging means this capacitor will be having a potential which is less. Okay, so it is initial potential. It was at zero, then it is charging, then it is coming discharging, discharging. After discharging, it will be charging with that opposite polarity, minus V saturation. So once it is going beyond this minus V saturation, okay, so the potential across this capacitor now it is minus VLT. Then it is going more than that, that is higher than minus VLT, which means that in magnitude, if you consider the direction also, it is going less than VLT value, that is lower threshold value. So once it is going less than that VLT, what will happen to the output? Output will shift from the minus V saturation to plus V saturation. Okay. So in this case, the output is going to shift from, so until that point, it will be in the same state, that is, it will be remaining in that minus V saturation. Once it is reaching the capacitor, across that capacitor, the potential is going to be at VLT, or it is going beyond that VLT, less than that VLT. Then the output is going to shift from plus V saturation, sorry, minus V saturation to plus V saturation. Why? Because at that moment, your non-inverting terminal will be having more potential than the inverting terminal. So in that case, this will again go to the plus V saturation and plus V saturation beyond that lower threshold value. Then, so then it is staying that way. Then also the capacitor starts charging, and again it will discharge, and this process continues. So the complete circle like this. So you can complete this capacitor will again charge, okay, so that once it is crossing that threshold value, then this output again shift from plus V saturation to saturation, and this will continue. So because of this, we can have a continuous square wave at the output. Uh, then we can make use of this particular circuit for relaxation oscillator. Relaxation oscillator. Relaxation oscillator means oscillator without having that sign. That kind of oscillator. Relaxation oscillator. And in this case, this can be used as a relaxation oscillator uh, by as this astable multivibrator. It can be also used as a, it can be used as a relaxation. Okay, so it will give you a continuous square wave as the output. Okay, so we are not giving any. In this case of Schmitt trigger, what is happening? We are giving a sine wave as input, and we are getting the square wave. Here we are not giving any input, okay, but we will get the square wave of this oscillation having square waveform which is having a square wave. Okay, so we can use this kind of a circuit for relaxation also. So this is the basic operation. So I only discussed about first case here. So the remaining you can complete, I think, because we have discussed the first case. Because of that feedback, the capacitor charges and the output shifted to the minus V saturation. And when this happens and the capacitor starts discharging, and it will be charging in the negative potential. Okay, and when it is once it is less than that lower threshold value, then it will go to the again plus V saturation. That you can write here. Okay. So I'm not going to write that all those part here. So you can complete that when what happens when the capacitor discharges and goes less than that of VLT. At that time, it will shift to plus V saturation. That you can write it. Now we will go to the monostable multivibrator. We will discuss that also. Then plus monostable. Okay, we have one equation here. Derive. We can say the time period of this square wave. Time period. Sometimes they will ask you to design this stable multivibrator with some time period. So this equation is also. So the time period of for the square wave that you have generated, T will be equal to T will be equal to 2 times RC into natural logarithm of then of 1 plus beta divided by this is the equation for that time period of your square wave. It's generated by using this Astable Multivibrator. Okay, so this beta, beta is R1 by R1 plus R2. Okay, so if you use this equation, then you can find out what is T time period for that square wave. So sometimes in the problem section they will ask to design a stable multivibrator with the time period of this or frequency of this. Then you can calculate that T, and you put appropriate R and C values, then R1, R2, R3 values. Then you can design that particular. Sometimes they will give that values, or sometimes some values they will give, or you can take R1 equal to R2 equal to R circuit in these equations, and you can calculate beta values. Then take so accordingly we have to adjust the value of T. Okay, so they will be given T equal to some values, and according to that you have to set this R1 R. Now we'll discuss monostable multivibrator. Monostable multi one more thing here I have to say why it is called as astable. Astable because we are having both of these tables, stable state and unstable state. For example, this is your unstable state. When you are considering states, you are having both that unstable state and stable state in case of a stable multivibrator. Okay, so that is continuously changing between your unstable and this wave is also which will be continuing. Okay, so that the continuously changing this state will be continuously changing. Okay, so here we have continuous two states. Right. So the output is continuously changing between these two states. That's why it is called as stable. If you consider monostable, then only one stable and unstable state will be. That's why it is called as monostable. In this case, we have only one stable. That's why it is called as monostable. Anyway, so in this case, circuit is a little more modified. So we have this circuit. We have diode also. We are having same circuit as for that stable multivibrator. Three small multivibrator. This is your feedback resistor. Just in the test. Okay, so then we had that capacitor here, input and capacitor is of a stable, just discussed, but is grounded. Here we have, along with this capacitor, we have diode which is parallel to this capacitor, like this. So this is the only difference that is having for this monostable multivibrator as compared to the astable multivibrator. So we have this diode. Okay. Now what will happen to this potential? Let's say this is your output, and your output is at plus V saturation initially. So in this case, what will happen? Let's say this is your inverting terminal. Now what will happen? When the output is plus V saturation, let's consider initially the output is at plus V saturation. What will happen? The diode becomes forward biased. Okay? This diode will become forward biased because this is positive. Let's say V out is equal to plus V saturation now. So once it is, this one is positive, which means that the diode this side is positive, this is negative. So this diode is now forward biased. Forward biased means it will conduct this current, this diode or the potential that is in the forward biased configuration. Okay. So in that case, the potential across this capacitor will be equal to the potential across this diode. Okay. The potential will not be larger than this diode because if this if you apply some current through this circuit, then it can go through this direction, it can go through this capacitor also. Okay. So maximum potential that this capacitor will be having is potential across this capacitor when you are plus V saturation, your output is equal to plus V saturation. Okay. So this potential across the capacitor will be equal to that of diode potential across this diode. So at this inverting terminal, when you are having output is equal to plus V saturation, at this inverting terminal we'll be having a potential which is equal to the potential across this diode. Okay. So that we will first draw with the explanation. So when I say this explanation, you write down in your notebook also, because I'm not going to write that. Let's consider that diagram. Let's say this is your output axis. Output, your right. Now let's take this is your plus V saturation. Plus V saturation. This is, so here you have that plus V saturation. And you are also having upper threshold voltage, VUT here. Here we have that VLT, lower threshold level. Okay, let's consider your signal, which is at the this is at plus V saturation initially, at plus V saturation. And in this time, when your output is plus V saturation, as I said, the diode will be positive here, negative here, so that the diode is positive, forward biased. Okay, so that the current can flow through this diode. Potential across this capacitor will be equal to potential across this. Okay, so in this time, if you draw that, I will just so this is your VUT and LTs. So your output is now plus V saturation, and your capacitor is having a charge which is equal to, sorry, potential which is equal to the potential of the diode. Okay. So in this time what will happen? Uh, Also, I think yes, yes. This is not the. But we have to apply some trigger here. That's how monostable action here. Okay, let's modify this one. Okay, I will just take. And this is your input voltage. Okay, so we have to give some trigger here. This is the input. Input means this is the trigger that we have to give. So we will be having some negative potential that we have to give at this input. So just modify the circuit like this, because we have to give some trigger that will make that stable state to the unstable or unstable to. So this is the circuit. Okay, we have to apply some trigger. So this is your trigger now, trigger signal that you have to apply. That is just a square wave pulse. So what will happen when in this case you are if you are considering that capacitor potential, what will happen to that capacitor? If you consider the maximum potential across the capacitor will be that of the diode, that will be constant, and that will be, so the diode, the capacitor will be having a potential like that is nothing but plus V saturation. So as this voltage at the inverting terminal, which is less than that of the non-inverting terminal, the output remains at the plus V saturation. Okay? So we can go up to that level. So I think better is to draw a little more. Because, so let's say that so now this inverting terminal will be having lower potential than the non-inverting terminal. Why? Because the non-inverting terminal, how much is the potential here? The non-inverting terminal here will be having a potential which is equal to plus V saturation into R1 by R1 plus R2. That is nothing but your VUT, upper threshold voltage. So this you can see here, this is the upper threshold voltage. The upper threshold voltage is much higher than this potential across that capacitor, which is equal to the forward potential drop across this load. Okay. So this upper threshold voltage is much higher than this potential across the capacitor, and this potential across the capacitor is equal to this potential at this inverting terminal. Okay. So this is less than that of the upper threshold voltage. So the output will remain in the same state in this case, remains in the same state, because your potential across that capacitor is same, and it is not going to change in this. This is also going to change. So this blue colored line, which is showing that potential across the capacitor, which is equal to the potential at the inverting terminal. So this potential, which is smaller than this upper threshold voltage, only when it is crossing that upper threshold voltage, we will be having that shift from plus V saturation to minus V saturation, as we discussed earlier. But in this case, it is not going to happen, because the potential will be always across, potential across this capacitor will be always equal to this potential across this diode. When the diode is in the forward biased condition. Okay, that is important, because the current can flow through this diode now. So this is a path which is given to the current. So it does not need to be going through this capacitor, because it already having does not have to go through this capacitor. So the capacitor will not get charged. So the total potential across this capacitor will be equal to the forward potential. Okay, so the capacitor will be having at the same potential. The input or the inverting terminal is having at the same potential, so the output will be remaining at the same plus V saturation. Now, if you are giving this trigger now, which is an inverting trigger or which is a negative trigger with the negative potential. So when you are applying this negative potential in this terminal, okay. So because of this negative terminal, negative potential or negative trigger that you are applied, this potential at this non-inverting part, potential at this non-inverting terminal, that is going to be decreased. Okay, and you have to apply this trigger in such a way that non-inverting terminal potential should decrease less than that of this potential across this capacitor, this value. Okay. And in that case, this means that your inverting terminal is now having more potential than the non-inverting terminal. Your inverting terminal will be having more potential than the non-inverting terminal when you are giving this trigger. So your trigger signal, I will draw that over. Trigger signal. Let's consider here you are applying. So you should apply that trigger somewhere here. So when you are applying this square wave as a trigger, this system, what will happen? So it should go below this capacitor value. Or I will just that. So the total potential now should go beyond below this capacitor potential across that capacitor. Okay. So when you are giving this negative trigger, you are having this much of potential. Oh, uh, So this is a negative potential, and we are having plus V saturation here. So if you consider that trigger here, for example, so it should go, a total potential should go below this value, so this value of capacitor potential across that capacitor. Then what will happen? Your inverting terminal now will be having more potential than the non-inverting terminal because of that trigger. So at that time, your output will become will be shifted to the minus V saturation because your non-inverting terminal is having lower potential than the inverting terminal. So your output will be shifted from plus V saturation to minus V saturation when you are applying that trigger. It will be shifted from plus V saturation to minus V saturation. And it will remain in this state when you are having this potential. Okay. So now what will happen to this particular? So because of that triggering, you are changing your output to minus V saturation. Okay. And when this output is going to become minus saturation, what will happen? Then your output is now it is minus V saturation. Minus V saturation. So in this case, what will happen? It is if you apply that minus V saturation on that output, you are getting minus V saturation on that output. What will happen to this diode? What will happen? Because you are having minus potential in this side at the output side, so that minus potential will be coming here, So now you are having minus potential on that side for your capacitor. You are having minus potential here. You are having positive potential here. Since this is a minus, which is coming from this output minus V saturation, since this is negative, now your diode will be in the reverse biased configuration. Since it is reverse biased, no current will flow through this. So this current is not going to flow through this. Okay, so entire current will be passing through this capacitor. So the capacitor starts charge. Okay, so in which direction? In the negative direction. So because we are having minus V saturation. So the capacitor will be starting charging in the opposite direction, like this. So it depends on that potential values and the capacitor charging. All those things will be determining this time period. So I'm not going to go it accordingly, but it is a rough sketch. So now the capacitor is going to charge in the opposite direction, negative direction as you can here. So once it is having a charge which is proportional to, or which is producing a voltage across that capacitor equal to VLT. Okay, because when the capacitor charges, it is having high potential across this capacitor. Okay, if you measure that potential, then that charging is increasing, potential also get increased in such a way that this negative terminal will be having again, it is going to cross this VLT value because the negative terminal potential is going below that lower threshold value now because of the capacitor charging. So when it is going below that lower threshold value, what will happen? The output will shift from the plus V saturation, minus V saturation to plus V saturation. I don't here it is wrong. We reach at minus V saturation. Here. This should reach here. So this will remain in this minus V saturation. And once this capacitor is having a potential across that which is going below this VLT, that is lower threshold value, your output is going to plus V saturation. Okay. So in this case, this will go to plus V saturation once it is once the potential across that capacitor reaches below that VLT, that is lower threshold value, it is shifting its output towards this plus V saturation. Okay. Now this once only this will happen when you are given that trigger, and in the remaining time this will the output will be remaining in the plus V saturation. And only when you are applying the next trigger only that is going to become to the minus V saturation state. So when only you are applying that uh, trigger signal, this is your trigger. So when you are applying this trigger, then only that is coming to the minus V saturation. Until that moment, it is going to be remaining in that plus V saturation state. Okay, so only one stable and one unstable state is possible in this case. Okay, when you are applying a single trigger, only one stable and unstable. So here, what is going to happen in the remaining case? What will happen? So this is capacitor is going again to the state, that potential. So until you apply the next trigger. Okay, if you are applying next trigger, then it is again coming down to the plus V minus V saturation. Okay, so we have a single stable and unstable state in this case. The same thing that we can do with the unstable position also. when you're having initially a minus V saturation position, your output is at minus V saturation initially, and you are giving some a positive trigger to that system. Then also the just opposite to this, that is also possible. That means you can change a stable state to an unstable state, or an unstable state to stable state by applying this trigger. That is in case of this monostable multivibrator. So we have here unstable state here, stable, and we have a stable state. So we can shift from stable state to unstable state accordingly, okay, by applying that trigger, and depending on your output voltage, output at what state your multivibrator is at the current. So depending on that, if you are applying a negative trigger or positive trigger, we can change the state from stable to unstable position by using this monostable multivibrators. Okay, so this is the action of the monostable multivibrator. I hope you understood this. Here also we have that time period, and in this case, don't confuse that time period, because we are not having a continuous oscillation here. We do not have a oscillation type signal. We are just having a square wave because of that trigger. Okay, so this is just the time. You cannot say this is uh, time period or something like that. We can say this is as a time duration of the pulse. So we are talking about this T. Okay, so that T will be given by the equation. I'll just write it as duration, time duration of the square wave, or we can pulse, time duration of the pulse. So that will be equal to, that will be given by T equal to, in this case it is RC ln, here it is 1 plus R2 by R. This is the time that is okay, so don't think that it is time period of the oscillation. We do not have any oscillation here. We just change its state from stable to unstable state, or plus to minus. So this is a time duration for this particular pulse. Okay. Just opposite to this also you can perform if you are considering initially your state as minus V saturation, and also that can do the same. So in that case, you will be getting something like this. Okay, so initially it will be at this minus V saturation, also minus V saturation. Then in between you will be having some plus V saturation because of that figure. That is also possible with the opposite plus V saturation. And this is also possible. Okay, so this is the action of monostable multivibrator. So I hope you understood, and you can write all the other things. I will just say one more time for the convenience of your note. So what is happening here? Initially, we considered that your circuit is having an output which is equal to plus V saturation. Okay. At this time, your diode will be forward biased because you are here having plus V saturation at this end, and that will make your diode forward biased. So your capacitor, across this capacitor, you will be having always uh, the potential across this forward biased diode. Okay, because the current can flow now. So the potential at this across this diode will be equal to potential across this capacitor. Both are having same potential, and will be having that same potential at the inverting terminal. So that is given by this particular blue curve, and that is less than this upper threshold value, and it is remaining in that same position, same potential, which is less than that of upper threshold value, until you will be then we are giving that trigger signal. And once you give that trigger signal, what will happen? It is a negative trigger signal, which is having a negative potential. And when you are giving that negative trigger, the potential plus V saturation at the output is going to be decreased which is going to be less than that of the potential at the inverting terminal because of this the potential across this capacitor. Both are same. So that the because of the trigger, the potential at this non-inverting terminal will be less than that of this potential across this capacitor. At that time, the potential across this inverting terminal will be more than that of the non-inverting terminal, and your output will be shifted from plus V saturation to minus V saturation. And this the output will be in that state minus V saturation as long as this capacitor potential which is going below this lower threshold value. And when this output is minus V saturation, as we discussed earlier, when this is minus V saturation, your diode is diode will become reverse biased condition, so no current will flow. So the capacitor will be charging in this stage, and because of that charging, the potential across this capacitor increased in negative direction. So this potential is increased, and once it is going beyond this lower threshold value, I'm talking about increasing means in magnitude it is going to increase. Once it is going less than that of the lower threshold value, okay, and at that time your non-inverting terminal will be having more potential, or we can say this when it is going this VLT beyond this VLT lower threshold value, your output is going to shift from minus V saturation to plus V saturation, as we discussed in the case of previous stable and so when it is going beyond this lower threshold value, your state is shifted from minus V saturation to plus V saturation. And that after that, it will be staying in that plus V saturation position because the, uh, then next after next trigger only we can go to the minus V saturation. So this is the action that is happening in case of a monostable multivibrator, and the T equation also we know. And sometimes they will ask to design monostable multivibrator of this much of period or the pulse duration. Then you have to choose the RC and R2R and use in such a way that you will get that particular T, and you design that circuit and draw the circuit diagram and put the value of R1. All those values you can put and find that particular circuit. Okay, so this is the this one is R1. So this is the explanation for this monostable multi. I think we have to cover Wheatstone with Wheatstone circuit, which is the Wien bridge oscillator. Okay, we have one Wien bridge oscillator in complete in this module, and then we'll go to the electronics. So if you have any doubt, you can ask.